Welcome to learn fundamentals of data structures and algorithms course. We are discussing searching algorithms. In the last session, we have discussed linear search or a sequential search algorithm. Given the unordered array of elements, say A1, A2, A3, etc., An, and one searching element, say X. The searching problem is to check if the searching element X is available in the given array or not. In case if the searching element is available, the algorithm returns the correct index where the searching element is available in the array. If not, that means in the unsuccessful search, the algorithm returns a value 0. 0 which indicates that the searching element is not available in the array. The second way of searching the searching element in the given list of values is binary search algorithm. In this session, we focus on what is a binary search algorithm and how to devise the iterative as well as recursive formulation of the binary search algorithm. First, let us devise the iterative binary search algorithm. The requirement of binary search algorithm is that the input elements must be in the sorted order. Suppose capital A is a one dimensional array which consists of n elements. Assuming the structure of the array is A1, A2, A3, etc., An, n elements are there in the array. The array elements satisfy this relationship A1 less than or equal to A2 less than or equal to A3 less than or equal to etc., less than or equal to An. That means assume that the array elements are in the sorted order, ascending order. Let X be the corresponding searching element. X is the searching element. The searching problem is checking if X is available in the array entries or not. In case if X is available in the given array, we need to determine the corresponding index, and the index should be returned to the calling place. In case if the searching element is not available in the array, what we have to do, we need to return a value 0, 0 which indicates that the unsuccessful search. Now we need to implement the binary search by, right, which means 2. The given list of array elements are divided into 2 ways, right. That means the range is divided into 2 sub ranges. For that, what we have to do, we need to have the variables. Initially set the variable first to point the first index. Consider this array representation A1, A2, A3, etc., An minus 1 and An. Since the array elements are satisfying this relationship, we can easily compare the searching element with the mid location in the array, so that we can divide the input range into 2 sub ranges. So set first is equal to 1 and the variable last is set to n. That means this is the first index or indices 1, 2, 3, n minus 1, n. The variable first is initially pointing the first index and the variable last is pointing the last index in the array. Having this initialization, first is equal to 1, last is equal to n, what we have to do? We have to find the mid location in the array. So, find the mid location in the array. Mid is equal to first plus last division to the lower bound value. So, compute the value of mid as mid is equal to lower bound value of first plus last division 2. For example, here this is the mid index. Now, mid index is pointing right this one. In this case, the searching element is compared with the mid location in the array. So, compare the searching element x with the mid location in the array A of mid. That means we are comparing two quantities, say x and y. When we compare two quantities x and y, we apply the law of trichotomy, the law of trichotomy. So, comparing two quantities x and y, there are three possibilities. X is less than y, second possibility x is greater than y, third possibility x is equal to y. These are the three possibilities when we compare two elements x and y. X and y rate may be equal, or x is greater than y, or x is less than y. Clearly, the searching element x is compared with the mid location in the array. So, when we compare x with the mid location in the array, suppose when x is equal to A of mid, in this case, what we have to do? We have to return a value mid, return mid, which means that the searching element is available at the mid location in the array. If not, if x is less than A of mid, then the search range should be reduced into say 50%. Since here the mid location is pointing this one, this is A of mid. Array elements are in the sorted order. Since x is not equal to A of mid, and assuming that x is less than A of mid, in this stage the search range is reduced to first to mid minus 1. That means there is a chance of finding x in the range from first to mid minus 1, since clearly x is less than A of mid. X is not equal to A of mid and x is less than A of mid. That means we need to check the value of x from the indices first to mid minus 1. Initial range is first to last, first comma last. This is the initial range. Even in the initial stage, first is 1, last is n, of course 1 comma n. This is the initial range. Assuming the size of the array is n, 1 comma n is the initial range. When x is less than A of mid, the range first comma last is reduced to first comma mid minus 1. So, in this stage mid minus 1, this is updated to a variable last. So, logically we have, if x is less than A of mid, then last is equal to mid minus 1, else if we can write here also else if else if x is equal to a of mid, else if x is less than a of mid, then else no need to check if x is greater than a of mid, because law of trichotomy, x is equal to a of mid fails, x is less than a of mid fails, ultimately here x is greater than a of mid. When x is greater than a of mid, what is the meaning? This is the range to be explored. X is not equal to a of mid, x is not less than a of mid, so ultimately x should be greater than a of mid, because x is equal to y fails, x less than y fails, the third possibility holds x greater than y. That means the searching element x is greater than a of mid. In this case, the search range to be explored is mid plus 1 to last. Since x is not equal to a of mid and x is greater than a of mid, there is a chance of finding the value of x in this range mid plus 1 to last. Now, mid plus 1 to last, here we are updating the variable first. First is updated to mid plus 1. So, here else first is equal to mid plus 1. This is the control logic of a binary search algorithm. Initially set first is equal to 1, then set last is equal to n, then find a value of mid. To find a value of mid, the entry condition into the control logic is first should be less than or equal to last. First should be less than or equal to last. So, when first is less than or equal to last, if the condition is true, then find a value of mid. Mid is equal to first plus last division 2. Then check if x is equal to a of mid, then return a value of mid. Else if x is less than a of mid, update a value of last, last as mid minus 1. Else if x is greater than a of mid, right, ultimately when x is not equal to a of mid and x is not less than a of mid, here x is not equal to a of mid and x is not less than a of mid. Algorithm binary search, this is the name of the algorithm. The algorithm takes the parameters a array comma n comma x. A array, this is a one dimensional array which consists of n elements. What is n? N represents the input size. The array elements must be in the sorted order. Here we are assuming that the array elements are in the ascending order. Structure of the array is a1 less than or equal to a2 less than or equal to a3 less than or equal to etc. a n minus 1 less than or equal to a n. That means the array elements are in ascending order. If x is equal to a of j, then return a value j. That means the searching element is available at the jth index in the array, then the index j is to be returned. Else return 0 when the searching element is not available in the array. During the unsuccessful search, the value 0 is to be returned. To implement this iterative logic, we are initializing the variables first is equal to 1, last is equal to n. As long as first less than or equal to last remains true, we need to compare the searching element with the mid location in the array. So, finding mid is equal to first plus last by 2, lower bound value first plus last division 2. Finding the lower bound value here first plus last division 2, then take a lower bound value. mid is equal to first plus last division 2. Now check if x is less than a of mid. If x is less than a of mid, the variable loss is updated, loss is equal to mid minus 1. If x is greater than a of mid, then first is updated to mid plus 1, else x is equal to a of mid. That stage that results in a successful search. So return mid. This is a successful search. The element is available at the mid location in the array. We can also write positively write the comparison if x is equal to a of mid, then return mid. Else if x is less than a of mid, then loss is equal to mid minus 1, then directly write using else we can write first is equal to mid plus 1. While starts here, while ends here, following the complete execution of the while loop. That means when the condition first less than or equal to last becomes false, we need to return a value 0. This 0 which indicates that this is the unsuccessful search. Closing curly brace, this is the end of binary search algorithm. So clearly when the searching element is available in the array, one stage this return mid returns the correct index. If the searching element is not available in the array, one stage this return 0 returns a value 0 to indicate this is an unsuccessful search. Let us verify the correctness of this iterative constructor with an example. Now let us verify the correctness of iterative binary search. Suppose n is equal to 8. Consider 8 elements in the array in sorted order, say 10, 15, 20, 25, 30, 35, 40, 45. Array indices are 1, 2, 3, 4, 5, 6, 7, 8. This is the array. Suppose take the searching element x is equal to 15. The searching element 15 is available at the second location in the array. Let us verify the correctness of iterative binary search. Construct the columns so that we can easily trace the algorithm first last, check if first less than or equal to last, then check if x is equal to a of mid or x is less than a of mid or x is greater than a of mid. To check these things, find a value of mid. Here mid is equal to first plus last division to lower bound value. Initially write first is 1, last is n is 8, first less than or equal to last, condition is true. Finding a mid value, what is mid? Mid is equal to lower bound value of first plus last division 2. 1 plus 8 9, 9 by 2 4.5, so mid is 4. Fourth location we are checking if x is equal to a of mid. X is searching element 15, 15 is less than 25. Since 15 is less than 25, the variable loss is updated. Update loss is equal to mid minus 1. First remains 1, loss is updated to mid minus 1, 4 minus 1 3. Now control enters again in the while loop, while condition first less than or equal to last is true. Finding a value of mid, mid is equal to first plus last by 2, 1 plus 3 4 by 2 2. Checking if x is equal to a of mid, x is 15, a of mid is a of 2, a of 2 is 15, 15 is equal to 15, condition is true. So the statement to be executed is return mid, current mid is 2. This 2 indicates that the searching element is available at the second location in the array. Likewise, if we take any of these inputs 10, 20, 25, 30, 35, 40, 45, the algorithm returns a correct index, so that these inputs result in the successful search of the algorithm. When we input A1, A2, A3, A4, etc., AN, these are the only successful search inputs to the algorithm. Inputting any other value which is not available in the array, that results in the unsuccessful search. Let us verify one unsuccessful search. Suppose x is equal to 55. Let us check if 55 is available in the array. 55 is not available in the array. Let us see how the algorithm returns a value 0 to indicate that 55 is not available in the array. Having the same headers, first, last, first less than or equal to last, mid, then comparison of x with the mid location in the array. Initially first is 1, last is 8, first less than or equal to last, condition is true, mid is equal to 1 plus 8, 9 by 2, 4.5, lower bound value of 4.5, that is 4. Now checking if x is equal to a of mid, 55 not equal to 25. X is less than a of mid, 55 is not less than 25. 55 is greater than a of mid, that is 25. Condition is true. In this case, the variable first is updated. What is first? First is updated to mid plus 1. So updating first as mid plus 1, 4 plus 1, 5. Last remains 8. Now control enters into the while loop condition, first less than or equal to last, condition is true. Finding a value of mid, 8 plus 5, 13, 13 by 2, 6.5, 6.5 lower bound value is 6. Now checking the 6th index in the array, 6th index the corresponding element is 35. Again it seems 55 is not less than or 55 is not equal to 35 and 55 is not less than 35. So 55 is greater than 35. First again needs to be updated. First is equal to mid plus 1. Updating first to mid plus 1, 6 plus 1, 7. Last remains 8. First less than or equal to last, condition is true. Mid is equal to 7 plus 8, 15. 15 by 2, 7.5. Lower bound value is 7. Checking the 7th index in the array, that is 40. Again 55 is greater than 40. Now first needs to be updated. First is equal to mid plus 1. First is equal to mid plus 1, mid is 7, 7 plus 1, 8. Last remains 8. 8 less than or equal to 8, condition is true. Mid value is 8, 8th element is 45, 55 is still greater than a of 8, 45. Again first needs to be updated. First is equal to mid plus 1. First becomes mid plus 1, current mid is 8, 8 plus 1, 9. Last remains 8. Since 9 is greater than 8, condition is false. First less than or equal to last, condition is false. Control comes out of the while loop. Then the next executable statement is return 0. Return 0. This indicates that the searching element is not available in the array. That means this results in unsuccessful search. So x is equal to 55, this is not present in the array, not present in the array. x is equal to 55, this results in unsuccessful search where x is equal to 15, this results in a successful search. So, clearly the iterative version of a binary search algorithm works correctly for all possible inputs, that may be a successful search input or unsuccessful search input. Clearly there are n successful searches, there are n successful searches, because if we input any of these n elements, ultimately it results in the successful search, and there are n plus 1 failure searches. For example, here n is equal to 5, 5 elements, say 1, 2, 3, 4, 5. Assume these are the corresponding array elements, indices 1, 2, 3, 4, 5. This is the array A. If we input any of these array elements 1, 2, 3, 4, 5, since n is equal to 5, this indicates that 5 successful searches, assuming that the array elements are distinct. If we input any value, right, in between minus infinity to 1 and in between 1 and 2, in between 2 and 3, 3 and 4, 4 and 5, this results in, and 5 comma infinity, this results in unsuccessful search. Minus infinity comma 1, right, the element is not available. In between 1 and 2, say 1.5, 1.5 is not available in the array, unsuccessful search. 2 comma 3, 2.7 not available in the array, 3.2 not available in the array, 4.8, 4.7, in between any value, right, 4 and 5 are taken as one possible input. 5 comma infinity, right, 7, 8, 10, any value, right, in between 5 and infinity, infinity, right, are taken as one possible unsuccessful search. So, totally 1, 2, 3, 4, 5, 6, 6 unsuccessful searches are there, unsuccessful searches. So, in general, for the input size n, we have n successful searches and n plus 1 failure searches. For the input size n, there are exactly n successful searches and n plus 1 failure searches. Now, let us devise the recursive algorithm to construct the logic of a same binary search. In case of recursive algorithm, we need to clearly specify the termination condition. The entry condition into the recursive binary search is the array indices, right, first and last should satisfy this condition, 1 less than or equal to first, less than or equal to last, less than or equal to n. This is the entry condition into the recursive binary search algorithm. See, when finding a value of mid using mid is equal to first plus last division 2, then checking if x is equal to a of mid, then return mid. Else, if x is less than a of mid, then last is equal to mid minus 1. Else, if x is greater than a of mid, updating first is equal to mid plus 1. This is the iterative version. This iterative version can be easily converted into the recursive binary search, where the recursive binary search takes the parameters recursive binary search A array x, right, as a searching element, we are passing the variables first comma last. So, the variables first and last are necessary. When x is equal to a of mid, then return mid, no problem. When x is less than a of mid, last is updated to mid minus 1. So, instead of writing right, if x is less than a of mid, then last is equal to mid minus 1. Here we need to apply the recursive call, make a recursive call with the updation of a variable last as mid minus 1. So, in the recursive call we need to pass the parameters, necessary parameters, say first, and the variable last is updated to mid minus 1, else first is equal to mid plus 1. Here we need to initiate the recursive call with parameter first as mid plus 1. So, mid plus 1 comma last. The entry condition is right, checking if 1 less than or equal to first less 1 less than or equal to first, less than or equal to last, less than or equal to n. In case if first less than or equal to last becomes false, then return a value 0. So, this way the iterative version is easily converted into the recursive binary search. Now, see the complete recursive binary search algorithm. Binary search recursive, this is the name of the recursive binary search algorithm, binary search recursive. Parameters are A array first comma last comma x. A is the one dimensional array which consists of n elements. The array elements are in the sorted order, increasing order. First and last are the variables, right. In the initial call, first is set to 1 and last is set to n. In the initial call, first is set to 1 and last is set to n. X represents a searching element. So, initially we need to invoke this algorithm as binary search recursive A array comma 1 comma n comma x. 1 less than or equal to first, less than or equal to last, right. Last is also less than or equal to n. The termination condition is right defined from this relationship, first less than or equal to last. If the condition becomes false, then there is a termination condition, or we can say the value to be returned is 0 to indicate the unsuccessful search. So, if last is less than first, then return 0. This is the indication of the unsuccessful search. As usual, right, as we done in the iterative binary search, find a value of mid. Mid is equal to lower bound value of first plus last division 2. Check if x is equal to a of mid, then return a value mid. This results in a successful search. If x is equal to a of mid, the searching element is available at the mid location in the array. So, this results in a successful search. Else if x is less than a of mid, then the search range is reduced to first to mid minus 1. This is the search range. For the initial search range, first comma last, we have made this initial call recursive binary search A array comma 1 comma n comma x. Now, since the search range is reduced to first to mid minus 1, the actual parameters are updated. Return binary search recursive. See, this is the name of the algorithm, right. Binary search BSR, binary search recursive. Same algorithm name is mentioned inside the algorithm. It results in a recursive call. Return binary search recursive A array comma first comma the actual parameter, right, the third one, this is updated to mid minus 1 because the search range is first to mid minus 1. Searching element, right, x remains the same. Else return, since x is greater than a of mid, then the search range is mid plus 1 to last. This is the search range. When we have the search range as mid plus 1 to last, so the first parameter is updated, first is equal to mid plus 1, last remains the same, x is a searching element. We can also declare, right, the array as a global one and the variable x as the global one, so that we can eliminate these parameters, right, in the formal parameter of this algorithm. Only, right, we keep, right, the variables first comma last. Declare a array as a global variable, global array, and x as a global variable, so that we can keep only two variables first comma last. Here, right, in the case when x is less than a of mid, pass the variables, right, first comma mid minus 1. Else if x is greater than a of mid, we can pass the variables mid plus 1 comma last. This is the recursive binary search. Clearly, when the recursion is terminated, here the condition is true, last less than first. When last less than first is true, then recursion is terminated here, so that the value 0 is to be returned. This results in the unsuccessful search. During the successful search, the value of mid is equal to, right, the value of, right, a of mid is equal to x one time. That stage, if x is equal to a of mid results in true, so that the value to be returned is mid. So, clearly in the recursive binary search algorithm, when there is a successful search, this return mid returns a correct index. In case if the searching element is not available in the array, this return 0 returns a value 0. We can also verify the correctness of the algorithm binary search recursive by taking sample value, say n is equal to 5, n is equal to 10. The recursive binary search algorithm also works correctly. If there is a successful search, the algorithm returns a correct index. For n plus 1 failure search inputs, the algorithm returns a value 0. When we analyze the binary search algorithm for 3 possible cases: worst case, average case, and best case. In the worst case, the algorithm performs a maximum number of operations that results in a theta of log n base to computational complexity. In the average case, the algorithm performs the number of comparisons that lies in between the best and worst cases. The average case complexity also remains theta of log n base 2. In the best case, the searching element is available at mid location in the array. So, after finding the mid in the first computational check, if x is equal to a of mid, condition results in true, so that the statement to be executed is return mid in this stage. Clearly, the searching element is available at the mid location in the array. So, it requires only one comparison. In the first comparison itself, the algorithm returns a value mid. So, this results in a constant computation, constant computational time theta of 1. So, the worst case complexity of binary search is theta of log n base 2, average case remains theta of log n base 2, best case results in theta of 1 computational complexity. Compared to the linear search algorithm, In the linear search, worst case complexity is theta of n, average case complexity is a theta of n, best case complexity is theta of 1. In the linear search, when the searching element is not available in the array, or when the searching element is available at the end of the array, worst case occurs. Average case, a performance of linear search is also theta of n. In the linear search, best case occurs when the searching element is available at the first location in the array. Here in the binary search, the searching element is available at the mid location in the array, then the best case occurs. Only thing is, the array elements must be in the sorted order, a1 less than or equal to a2 less than or equal to etc. an. Where in the linear search, the input array is an unordered array of entries. So, comparing linear search with the binary search, right, takes a theta of log n based computational complexity. Theta of log n based computational complexity is better than a theta of n computational complexity. So, binary search performs a faster search compared to linear search.